Welcome to part 3 of Variography with SAGE 2001. In part 2, we calculated 37 directional sample variograms using 89,419 blast hole samples from a shear hosted gold deposit. In this video, we are going to use SAGE 2001 to model all of those 37 directional sample variograms. I hope you enjoy the video. Once you have installed SAGE 2001 and the USB driver, you can start using SAGE 2001 by clicking on the SAGE 2001 icon that will be located on your desktop. I'll explain where and how you can download and install SAGE 2001 later. But for now, let's model some directional sample variograms. SAGE responds to your click by showing you a splash screen for a few seconds and then pops up the initial screen with two menu items. The Help menu item is self-explanatory. If you click Help, SAGE will provide you with a detailed explanation of the menu items on the current screen. It is context sensitive. In other words, the screen, the help screen that SAGE opens up for you will contain information that is relevant to the screen that you are currently looking at. A very useful feature. However, we want to load the file containing the directional sample variograms that we calculated in part 2. So we select on Variography, followed by selecting the menu item Model Sample Variograms. SAGE responds by opening the Model Sample Variogram Setup screen. It also has guessed at what files we might want to open here. So let's look at the input file, Sample Variogram. That's au.pli. You will recall that the PLI file contains the directional sample information, all of the directional sample variograms that we calculated in part 2. So we'll open that. What about the plot file? Well, there's an au.plt that was generated in calculating directional sample variograms. They're not too useful, so I will overwrite it. Yes, let's replace it. The report file. Well, there is a report file there called au.rpt. That report file was generated when we calculated directional sample variograms, so I really don't want to overwrite it. Perhaps I'll keep it around to remind myself at some point what did we do. So I'll generate a second report file called au2. And that'll give me a report on what we did to model the directional sample variograms. Okay, the analysis title, shear AU, we'll stick with that. Minimum number of pairs by default is 350. Maximum drift, ignore that box. We don't use it. Weighting scheme. The most popular weighting scheme is by default by pairs. There are several others, no weights and inverse number of points per direction. I would go with the default. It's by far the most popular. Number of structures, I would stick with 2. Use 2 all the time, even if 1 would suffice. There's no harm in having 2, and that way you don't have to guess. 2 will always do. Well, what kind of structure types? We don't have a great deal of choice. We have spherical or an exponential with the practical range or an exponential with the traditional range. My favorite is the exponential with the practical range, so let's go with that and see what happens. The next screen is called Rotation Conventions. This is where we set the rotation conventions for the variogram model. So for example, we have a number of different options, and you must choose an option that matches your Kriging program. If it doesn't match the conventions used by your Kriging program, you will get garbage out from your Kriging program. So what are these conventions? Well, they are explained by the numbers in the brackets here. So for example, let's look at the med system conventions. In the brackets we have Z, X, Y, L, R, L. Z means it's the very first axis that we're going to rotate around. We're going to rotate initially around the Z-axis. The second rotation will be around the X-axis. The third rotation will be around the Y-axis. Now, the direction for each of those rotations is given by the next three letters, left, right, left. So the rotation around the Z-axis will be left, around the X-axis will be right, and around the Y-axis will be left. You'll recall that the left and right hand rotations can be determined by using your hand. The right hand rule, for example, you grab the axes. If you want to rotate around the Z-axis, for example, you grab the Z-axis with your right hand. Make sure that your thumb is pointing in the direction of increasing values, and your fingers will show the direction of a right hand, positive right hand rotation. Similarly, the direction for a positive left hand rotation, you would simply grab the axes with your left hand. We have a number of different conventions. One of the ones that I really like or think is very innovative is the custom. It's also quite popular with programs like Vulkan and Gemcom and so on. So we see here the first rotation is around the Z-axis. You have no choice. It must be around the Z. But the second rotation can be either around the X or the Y. Okay, and it can either be left hand or a right hand direction. Okay, so let's make it right. The third rotation then can be either around the Y or the Z. And notice the third rotation is around the Z-axis again. This is the rotated Z. And that can be left or right. So this would be a ZXZ rotation, and it would be left, right, left. That's it for rotations. Next, SAGE opens up a parameters. This is the parameters, which includes the nugget, all the rotation angles, and all the ranges for each of the structures. This box is the first model structure, and this one is the second. Notice the sill, the box with sill. It has a value of 1 in here, and there's a check mark in this little box called fix. We're using the parallelogram. The parallelogram has a sill of 1. So I have put in 1 as the value and a check mark here. The check mark here fixes that value. It's constant and will not be changed by SAGE. So for example, we could fix each one of these, or if we leave them unfixed, SAGE will figure out the proper value for those. However, often people will fix the nugget, maybe by doing a down the hole variogram or something, and they come up with a particular value and they say, my down the hole variogram told me that the nugget is 0.30, and they want to keep that value in your variogram model. So this is how you would do it. 0.30, fix the box. SAGE will determine all the other parameters, leave the sill at 1, leave the nugget at 0.3, a useful feature. Well, for me, at this point, I don't have a down the hole, so let's just go ahead and fit it. It's very fast. The analysis is complete. So SAGE opens up with a plot file. Again, we'll click on Show the Pairs. Then I'll say Show the Fitted Curve. And I look at this, and initially what I see, oh, I'm not too impressed with this curve. It looks, you know, let's stop this thing here off and go back to some of these. That one, look at that. That doesn't fit very well at all. And if I keep going back here, what am I seeing? What's the matter with the fit? Well, it looks like a large number of these points are quite linear, and we are using a curved model to do this. Exponentials tend to be very curved initially for the first part of the variogram model. The spherical model tends to be more linear. So maybe the exponential choice here wasn't very smart, and I probably should have done spherical. So let's just look at a couple more to see if that, yeah, that's a good example. This is far more linear, at least up to here, you know, than a curved model. So let's go back and change that. So we close this, back up, and here we are. We got two exponentials. Well, we saw that those weren't the best choice, so let's put in some sphericals and remodel it. Yes, we're going to overwrite that. Yes, we'll overwrite that. we're going to do the same custom here and same fix, and so we say go ahead and fit it, and it does that. Well, this looks a little bit better. So auto off. So yeah, you know, previous. Well, that looks better. Definitely fitting a linear model here seems to be quite a bit better. I'm bothered by this first point here, though. This is a kind of a screwy point here, and I actually would like to get rid of those. One of the things I notice is how many pairs are in there. 11,666. If I look at some of these other ones, let's go to another one here. 11,000, let's say 12,000. Whereas all of these, this has 76,000, 94,000. You know, this one is 147,000 pairs. So I'm tempted to say, look, if you got to have at least 12,000 pairs, else don't use that sample variogram point. And if I do that, I'm going to get rid of this. But perhaps I should have a little bit more justification than saying, I don't like the look of it. So let's see if we can figure out some reason why we really might want to get rid of that thing. And to do that, I'm going to go look at my report file from when we calculated, and I don't want to look at that one, that's when we calculated the directional sample variogram. So I want to open that with a little different editor here. And that is my Ultra Edit. So here we are. This is when we calculated it. You remember all the data we had from calculating it. And I'm going to look at that azimuth 45 degrees dip 0. One of the things I want to look at is the mean. Remember we talked about lag statistics. The global mean here is 0.57 grams per ton, and the standard deviation essentially is 0.9 grams per ton squared. Okay, if our sample variogram point, if this sample variogram point here is representative of the complete sample domain, then the mean of the pairs at the head and the mean of the pairs at the tail, and likewise with the standard deviations, should be pretty close to the global mean and the global standard deviation. Well, if I look here, I see it's 0.45. Doesn't compare very well with 0.57. And 0.4545. This is the mean at the head, the mean at the tail. The standard deviation is 0.62, 0.61. That doesn't compare very well either. Look at what happens when we go to a few more pairs here. Now we see 0.58, 59, 68 when we have a lag distance of 12 and so on. So so what's happened here is that I can justify elimination of this point because I'm saying the statistics of these 11,666 pairs are not representative. They're not close enough to the global mean and the global standard deviation, and so therefore I feel their variogram value that we're getting out of it is also not representative of the spatial continuity globally across our sample data set. So I'm going to throw it out. So how can we do that? Well, let's move this guy out of the way. We close this. We go back here and we say I gotta have 12,000 pairs, otherwise forget it. Okay, we're going to overwrite it. Same thing here. We're going to fit it. Fit that. Bingo. Here we go. And now what have we got? I got, it looks a little better to me. Fits all right. Okay. That's about as good as we're going to get it. Some of these pair of directions here fit pretty nice. Okay? So that's our model. SAGE also provides a number of external files that are written to your working directory. So for example, my working directory is C:variography, and here you can see that SAGE added a file called gam.ps and another one called rows.ps. So let's look at and see what these are. PS is a PostScript file, right? So if I click on Open PS, we'll see that it's basically covers the variogram models for all directions. So here we have the azimuth 45, dip 0, and we can scroll through these things. These are excellent documents for putting in the appendices of a report and as backup material for your professional work. There is another PostScript file called rows.ps. So let's look and see what's in rows.ps. Well, we start off by getting report on the variogram model parameters. There's the title, shear AU. It's user-defined rotation conventions. Then we have a summary of the nugget and the two coefficients, 0.447, 219, and 334. Then we have the first structure, which is spherical, the second structure, which is spherical. And then it tells us left hand, right hand, left hand, and we can see that it's a Z, X, Z, with the rotation axes, and then we have the ranges along the Z, X, and Y. And the same thing for the second structure, left, right, left. And we have the axes Z, X, Z, and again the ranges. And there are the rotation angles there. This is a summary of what the final azimuth and dip should look like. And maybe you can make heads or tails out of this, but I find it a little difficult to try and visualize what my anisotropy models look like in 3D space. But SAGE has some diagrams here which can help. This is something called a rows diagram, and this is for structure number 1. And this is a rows diagram of all the ranges that are dipping 0 degrees. So these would be the horizontal ranges. So we can see from the shape of the ellipse that it is more or less parallel to a strike of 45 degrees, which is what we want. Then we can, that's the first structure. If we click on this, this is all a rows diagram of all the ranges that are dipping 30 degrees. And notice that we have longer ranges going down to the footwall side. This indicates that there is a dip in this model, and the dip is in the direction 135 degrees. So that would correspond to what we know about the geology of the ore deposit from our exploratory data analysis. And finally, we're looking at a rows diagram of ranges dipping 60 degrees, and we can see that the ranges are longer. Down dip in that dip direction again is about 135 degrees. Okay, that's structure number 1. Structure number 2 we see has a much more severe anisotropy, but the strike is at 45 degrees. And if we click on this, we can see, oh wow, it has a very nice down dip. The dip direction again is about 135, which corresponds to what we know or what we learned from our exploratory data analysis in part 1. Okay, then we get some additional diagrams to help us understand or visualize what our anisotropies look like. And we start off by looking at this reference cube here with a north arrow through it. And we cut this cube with 3 planes, A, B, and C. And we imagine that within this cube we have an ellipsoid. In fact, we have 2 ellipsoids, which are the ellipsoids of our variogram model. And so when we take a slice through this cube, we would be cutting a slice through those ellipsoid models, and then we plot that slice in these 3 sections. So you can see there's nothing plotted on the section level map A, nothing on level map C. It's all on B, which means there isn't a lot of vertical extent, and we can see from B the strike of the major axes, the orientation, which is about 45 degrees from north. So that corresponds again to what we know from exploratory data analysis. Here's that same cube, and this time we are slicing the cube with sections as shown here, A, B, C, and our 3 planes, A, B, C. And so you can see that this corresponds to a dip, and the dip direction is again about 135, if you can imagine. Visualize that. And so again it fits. So that helps us see, and this is true for both structures, although we see the dark one, the little structure in the center here, has a little steeper dip than the exterior one. This one, again, we're looking at planes that are cut through our reference cube here, parallel to the strike, or parallel to north, if you will, sorry. And we see here, oh my gosh, there's also a dip to the south, which is something that we didn't recognize in our exploratory data analysis. So that's interesting. The variogram model and the directional sample variograms have picked up additional information about the pattern of spatial continuity that we didn't learn from our exploratory data analysis. Finally, I'm going to show you something here that's a little extra. This is not part of SAGE. It's a little tool that I have, which is that I'm going to provide to you in addition to SAGE. If you purchase SAGE after viewing this video, I will throw in this tool free. This is a tool then that enables you to view the ellipsoids in 3D space and rotate them. So let's see how it works. We're going to open up a command window. There's our command window. And we'll need some variogram parameters. So I'm going to pick up rows.ps. We'll slip that down. So here's my variogram model with all the rotation angles and ranges. So I'm going to put those into this program and visualize what these models look like in 3D space. So let's start by typing in SAGE Viewer, and it says, okay, SAGE Viewer is a program to rotate and view variogram models by Isaacs and Company. You can see it's been around for a while, 2009. Well, our case here, we have ZXZ. So we have a choice of ZXY, ZXZ, or ZYZ for the order of axes to be rotated. Ours is ZXZ, right? Okay, then it says, warning, ZXZ and da-da-da-da. And it says, enter the rotation angle followed by a R or L, upper or lowercase l. No spaces. And this is to tell it whether the rotation angle is left or right. Okay, so let's do that. So first we go to the first structure here. The length of the x-axis is 35. The length of the y-axis is 12. The length of the z-axis is 38. The first rotation around the z-axis here is minus 27 left. Then we have minus 23 right, and followed by minus 25 left. That's the first structure. If we didn't have a second structure, we just follow with a bunch of zeros here, and then it would only plot one ellipsoid. If we have a second structure, we can enter in its data, and it'll plot both ellipsoids. So again, the range on the x-axis here is 660. The range on the y-axis is, let's say, 26. And the range on the z-axis is 197. Now the first rotation around the z-axis is minus 53 left, followed by minus 43 right, followed by 6 degrees left. Okay, that's it. So here we are. I'm going to open up this screen. This is a viewer that you may not be totally familiar with, but it's very, very easy to use. I can start off by saying we want to study this object here, and then I have a rotation button, a pan button, a plan view button to move in or out. So for example, if I do this, I can move in or out like that. Okay, I can roll and rotate. So these things here are our axes. So for example, if I rotate this thing a little bit like that, and maybe a little bit like this, okay, so you can see, so there's the x-axis, there's the y-axis, there's the z-axis, and there's our ellipsoid with a long structure. So, okay, so there, we got it. Now if I turn this a little bit like this, you can see that the strike of this thing, or maybe if I move it like that, anyway, we play around with this rotation saw, and you can see that, okay, it does dip on an azimuth of 135, or if you will, and the strike is more or less between the x and the y-axis, so it's 45 degrees. So we get an idea. Now in the center there, very tiny, is our first ellipsoid. If we wanted to explore that in a little bit more detail, we could just plot the first ellipsoid only and not the second one, and then it would show us what we've got. So this is a very useful tool for looking at the orientation, if you want, and figuring out how does this thing fit in our Cartesian coordinate system. And then once we understand this, of course, we can see, oh yes, this does match our geology. And if we get to this point here, we're totally mixed up and we don't know where anything is, we click on that, bingo, we're back. This is the z-axis coming straight out of the screen right at us, right? So if we rotate it like this, you can see there goes the z, there comes the x, there's our plane, and then we can rotate it like this. So there's our 45, our 50-degree dip if you want. So there we go. You can also see that it's kind of true for our little inner ellipsoid too. It's kind of steep. It's a little steeper dip, but it strikes and so on is about the same at 45 degrees. So this is a useful tool. I throw this in free. If you purchase SAGE 2001, if you really want to know how and where to buy SAGE 2001, go to www.isaacs.com. Thank you. Hope you enjoyed the video.